not use temperature in order to thermal excite more atoms to the excited state than those left in the lower energy state. That means the following point must be true. Whenever you have more atoms up here than down here, you must drive the system out of equilibrium. And that opens up a new part of physics that usually is not covered in undergrad. That is non-equilibrium physics. You drive it out of equilibrium and then see how the system relaxes back to equilibrium. That is a big topic. That is the ordinary situation that I wanted to pick in this cartoon figure. So I have an ordinary material, a medium called an absorbing medium, because usually I will have N1 bigger than N2. Now, if I have an incident radiation EM wave go through this sample of length L, even we have stimulated absorption, stimulated emission, all these processes, due to the fact that we have this more in the lower state, more absorption will happen, right? And therefore, the outcoming beam will lose photons, each of this absorption, all right? So that's why the cartoons, this is weaker in amplitude than that. The amplitude, the intensity is proportional to the number of photons you have. That is the ordinary situation. And for those of you who like mathematics, you can try to work it out. If you have the intensity, here I use the frequency mu, that is the F, okay? 0 means this position, L means that position, okay? And then you can think about a tiny slab first, dx, for example, okay? And then you can try to see how many absorption will occur. That must be proportional to the number down here. And then how many emission will occur, that must be proportional to the thing up there, okay? And then it must be proportional to the rate, okay? But that rate will be the same. And then if you want to calculate how much energy is taken out, that must be the energy of the photon. So at the end, you will find that you can set up a differential equation if you consider a thin slab, and then you will find the solution to be decaying. That is a well-known optics rule. So you pass a beam through a sample length L, the other side get decayed, okay? And this factor, decaying constant, is proportional to N1 minus N2. Therefore, this is positive in ordinary material. And then there is a stimulated rate, and we know it from quantum mechanics what it is, okay? And then some energy. Therefore, if we want to have something called the gain medium, it is also called an active medium, it's also called an amplifying medium. The whole point is that if you want to get something rather strange, this is your input wave, this is what you get out after length L. It is even bigger than that, that is a gain medium. You must do something like this, N2 bigger than N1, okay? So now, you can work out the mathematics all the same, only that this becomes a positive number and that is related to the previous discussion, only that you need N2 bigger than N1, okay? But as I already mentioned, you cannot achieve that by thermal equilibrium processes. You cannot put it into a big heat bath, more energy in, more will be excited. The most you can get is N1, N2 approaches N1, okay? Therefore, you need something cleverer to put more atoms in N2 than N1, in 2 than 1. The name for this scenario is called population inversion. To achieve it, that takes something like 40-something years after Einstein's work. So that's why I said it is more than just saying Einstein invented laser. The first one that can do it is the ruby laser. Before that, lasing can only be achieved in the microwave frequency. That is the point that I tried to make in the previous hour about the omega cube 1, okay? It's easier to get microwave because that excited state is not too far away. Therefore, the spontaneous emission will not occur too readily and allows you an easier possibility to put more atom in the excited state than in the lower energy state. However, for optical range or even infrared, that omega will be too high, okay? Therefore, you need some clever invention in order to achieve population inversion. That has to do with the spontaneous emission rate. And Charles Townes received the Nobel Prize for this work. He also had the idea of how to make it into the visible range. So the first one that is in red visible range is this ruby laser. And ruby does not play the role for lasing. Ruby is this kind of a sand stuff, alumni, okay? But it's not the important point. The important point is that less than 1%, 0.5% or so of chromium impurity. The active thing playing important role is the energy levels of chromium 3+ ion. It has D3, I think 3D3, meaning in the D states, there are 3 electrons there, okay? So, and also these ions live in a solid, in this Al2O3, okay, this ruby. And it is this chromium ion giving the ruby the beautiful color due to optical transition. So the really important levels come from chromium ion. So let me briefly, in a cartoon way, summarize to you what is the idea behind this so-called 3-level system. First thing, this 3-level, this 3 is just meant to be representative. Actually, it may be a group of level in this number 3 thing. Not only one, but a group, okay? Usually it's a group. The idea is as follows. At equilibrium, that is not lasing yet, due to usual difference in this may be EV level, and thermal energy is just 0.05 EV, okay? That is a number to keep in mind. Therefore, thermal equilibrium room temperature, you have some ions, some atoms usually in the lower state. And now you need to find some way called pumping. I will discuss how in the next page, in order to suddenly excite a lot of this atom to the excited state. So after something is done to it, called pumping, there are atoms in this excited state. The design is that state number 2 in this free level is a metastable state, meaning you select something that this transition is only weakly allowed, not readily, to keep the atom there, basically. But we need a third one in order to achieve population inversion. The design is as follows. This group called number 3 can readily go into number 2 by allowed transitions. Okay, so once you have atoms in 3, it can easily go to 2. Of course, some of them will even go to 1, okay? But that doesn't hurt as long as this is fast. And therefore, a short while, okay? That has to do with the lifetime, okay? A short while after pumping, you have more atom in level 2 than in the ground state level 1. And it is at this moment that you can achieve this criteria for a gain medium. And then you have to design something that you have some light moving around this gain medium so as to stimulate these atoms to come down as stimulated emission, okay? The intensity will grow and grow, therefore that rate that is proportional to the U of omega will grow and grow, therefore you will have more and more stimulated emission coming down. But soon it will stop because once atoms come down, you will have this ordinary situation again, then no more lasing. That becomes a loss medium because there will be more absorption than emission, okay? So that is the key idea behind what is generally called a class of lasing system called three-level system. The first ruby laser goes as follows. This is a solid rod, ruby, inside which there are some chromium impurities scattered throughout. The concentration is low. There are some deep trap actually. So, and then because it's a solid, it is easy to make the two sides very, polish it very well. So they work as mirrors. One end has a slightly less reflectivity. That means some light will leak out. The other end is nearly a perfect mirror. This design is to trap some light already emitted inside which it goes back and forth. This design is called a resonator to set up an oscillation. It's called laser oscillation, so that more and more stimulated emission will come out. And you see something like a flash lamp is enclosing this ruby rod. That is the pumping device. So you use electricity, make this light, boom, shine on it. Then quite not selectively, just give energy to all these atoms and see where they will go, okay? So hopefully some will arrive at this and then it will fall down and then you have population inversion, that's the point, okay? So separating the processes, the pumping is go to a group of state called 3, then spontaneous emission to 2, and that is a slightly longer lifetime, it can come back down, okay? So that is the whole idea. And this is a very particular wavelength. So if you buy a ruby laser, you will get this. It can make very strong, okay? So industrially, it is used in many applications. It can cut things sharply, things like that. So if we put everything together, that is the whole figure, okay? And the instantaneous output is pretty big. So it is a nice laser. Nonetheless, there's one drawback. A drawback is that it only gives you a pulse, because once N2 becomes bigger than N1, lasing stops, and then you have to pump it again. Secondly, you need to cool down the system quite a bit, okay? Because you pump it with intense flash of light, therefore you need some 水冷, you need water to take out some heat. Because of this pulse laser limitation, another class of laser is called CW laser, or continuous wave. The idea is how we can keep lasing occurring, okay? If you look at the free level, the lower level is usually the ground state, and the ground state, even at equilibrium situation, is the most populated. Therefore, N1 is always rather big, and that is a problem, because we want the lower one to have a fewer population than the upper one, okay? So the idea now is not to use 3 level, but use 4 level. But 4 is just a name. Usually, again, this may be a group, all right? The idea is not to use the ground state as the lower level of the lasing process. Instead, choose a pair, E3 and E2, inverse populate 3, and then use 2 as the 3 to 2 transition as the lasing action. Because we can selectively pick something like E3 is metastable long lifetime, E2 is short lifetime, thereby once lasing come in here, this will automatically, spontaneously come down and clean up the level 2. So it will keep very few atoms at level 2. Thereby, continuous population inversion can be kept. That's the idea. So pictorially, on one page, the idea is as follows. At equilibrium, again, it is all the atoms there. You find some way to pump it. The pumped atom, because not selectively, usually, it may occupy many different levels. The important point is that these atoms in level 4 will come down very readily in this time scale. At the same time, those populated here will also come down to the lowest level readily. It's short life. Therefore, in a short while, the 4 will go down to 3, 2 will empty itself, thereby inversion in population is achieved between 3 and 2. And when some emission started to occur, there will be light in there to stimulate more emission. Okay, so that is the way to get continuous wave, not a pulse. Usually the output is weaker, but it's continuous, okay? So to put the whole thing together in one figure is something like that, okay? You pump, and then you come down, and then rapidly clean up level 2. How to make it? Here's one example. There are many more. This is a gas laser, a bigger tube, okay? You have helium atom mixed with neon atoms, okay? Two kind of impossible system for optical thing, very inert. But it so happened that there are energy levels in their excited state that we can make use of for pumping. I think that is the reason. The atom that is responsible for lasing is neon. Helium is for pumping. So let's see how it goes. We have a lot more helium responsible for making collision. When helium excited atom collide with neon, some energy will be given to the neon atom to excite the neon at the right energy. So it doesn't look like a 4-level system, but it works as a 4-level system. It goes as follows. For helium atom, we already considered the ground state in the previous module. We also consider the excited state 1s2, 2s, 1s1, 1s2. So put 1s, 2s, and then we have singlet, triplet, all these kind of things. Okay. Now, one of them has an energy that is 20 eV higher. Okay, and that is a lovely energy. So one can use many methods, electric discharge, or collide it with electrons so as to excite helium atom to this particular state. All in all, it means this excited atom carries this energy. Then in the atomic gas, some of these helium atoms can collide with neon in its ground state. When it does, because neon has a group of excited state that is again 20 eV high. By doing so, occasionally, not very often, okay, the collision of helium with neon will give this 20.6 eV to neon. And then the neon atom is now populated here. And that's nice, okay? And that is how population inversion is achieved in this particular laser. And then it will come down to this level 2 for stimulated emission. And then this is a rather short lifetime level. There are many places it can go, okay? So therefore, it will clean up the population here readily and come down either or through an intermediate level. Therefore, inversion can be kept between 3 and 2. So this is the cartoon picture, excited by collision, transfer it, and then lasing automatically clean up this excited state. Okay. A more popular one in recent years are the semiconductor lasers, the one that we use in lecture hall, things like that. Okay, and then it is the same idea, but we have solid states. We have semiconductors. In semiconductor, the basic idea is that we have a group, not only discrete state, because we have many atoms together. Then we have a group of states for electrons. Then we have a region called band gap in which there's no state at all. And then we have another region with many states. These are called bands. These are called band gap. This is electron states in a solid. So it's rather similar to atom, only that atom has very sharp allowed states. But when we put many atoms together, this has a state, this has a state, they start to interact, and then they will spread up into a group of states called bands. So we can think about this as a 2s band, 2p band, things like that. That is legal, and that is true, actually. Now, what is semiconductor? Semiconductor has the following properties. When we fill the electrons into this state, sooner or later we run out of electrons. We fill all electrons in. A semiconductor has the following property. It fills all the way completely to a certain band, and that band is called the valence band. And then there's a gap, and the band that is right after it is completely empty. Okay, so 100% full, 100% empty, separated by a gap, and that is what insulator and semiconductors are about. Okay, you see, Pauli exclusion principle has already been applied here. We fill electrons into the states. No two states can occupy the same state. Okay, no two electrons can occupy the same state. Thereby, it must go up in energy. Therefore, we can say at the end, one band is completely full, gap, and completely empty. All right. Now, if the gap is too large, something like 3 eV or above, then it is an insulator. If it is less than 3 eV, then it is a semiconductor. Okay, so no key difference between an insulator and a semiconductor in terms of quantum mechanics. And you must appreciate one point here. It is quantum mechanics, no more. Okay, quantum mechanics plus how to fill electrons in Pauli exclusion principle that explain why we have conductors, insulators, and semiconductors. Basically, 99% of all the matter that we encounter in our daily life. The remaining 1% is a superconductor. But you don't see any superconductor in your daily life, okay? Until, well, unluckily you go into a hospital, the semiconductor magnet may be in the MRI machine. Otherwise, that is basically all the materials. And if you don't know quantum physics, you can't even explain a little bit of materials, okay? That is the story about quantum physics explaining matter. Now come back to semiconductor. Semiconductor, the gap is usually about 1 eV, okay? Silicon is 1.1 eV, so you know silicon is the typical semiconductor. Now, how to achieve lasing then? Then we rather ironically, in the semiconductor industry, the first thing is to make it very pure. So for example, silicon, make it very pure. I think some of you know, right? In recent months, the whole world has a shortage of very pure semiconductor wafer. Do you know that? Many phone companies, all this high-tech company, they are, you know, shopping for this semiconductor wafer for their products, okay? Because of COVID-19 shutdown, a lot of reasons, okay? Some political, but that is a fact. So, but the first thing is to make it very clean and then make it dirty. That is the tricky point. By making it dirty, it is intentionally making it dirty, something called doping. That is to say, you select some particular kind of impurity and put it into a clean semiconductor. There are two ways to do it. One way is to add some extra electrons into the otherwise empty conduction band. That is called n-doped superconductor, semiconductor. An example is to pick phosphorus impurity into silicon. Okay, so that is N-type. You replace some of the silicon atom by phosphorus, and then how many you put in, then how many electrons you can put it up into this otherwise empty conduction band. The other way to do it is to put boron into silicon. In this way, boron can take some electrons out from this otherwise full valence band. I represent it by some empty circle here. Those are the empty, not occupied electron states, okay? So boron has this ability, take something out of the band, okay? And that is called p-dop. In solid state physics, you will realize this few electrons in the conduction band can conduct, can move freely. Also, these few unoccupied electron states can also move freely. They are called holes in a funny picture, but I don't want to get into that here. I just want to stay in the electron idea. They are unoccupied state. But this unoccupied state can move around in space. Well, of course, due to the motion of the electrons, okay? So now, if we put these two things together, an N-type on one side, a P-type on another side, we have what you may have heard about PN junction. So think about it. It is like this guy, if this thing is close to it, okay? I put this thing here, for example, okay? You see this guy, suddenly look at this thing, there's an empty state for it to fall into it, right? Lower energy, like it, right? High energy, like excited state, lower unoccupied state, nice. We'll go into it and make an emission. And in doing so, you can get light out. That is the mechanism for light emitting diodes, okay? Now, if you do it, you design your device correctly, you can say, now, don't come down first until I tell you to come down, okay? So the electrons will be collected there, inversion, population inversion, and then when they come down at the same time, then you will get semiconductor laser. So that is the idea behind semiconductor solid state lasers. So one final remark. In this module, what I want to convey in the more academic one is to introduce time-dependent perturbation theory. We don't do a lot, we just do the lowest order, first order. But you will see that is already very useful. We can understand atomic spectrum. You must appreciate, again, atomic spectrum is the experimental result that had driven the development of quantum mechanics. We started off with the Balmer-Lyman series so that people start to worry about why discrete lines. And then we have Bohr model, and then we have Schrödinger, a first paper solving the hydrogen atom, okay? Because of that, I really would like to introduce this time-dependent perturbation theory to you so that your knowledge will be completed in the sense that you also know how to explain why there are lines, selection rule, why some lines are brighter, because there is a formula. You can calculate this element, R12 square. If bigger, then it's brighter, okay? At least you have this idea. So that is the theoretical part. But the practical part is just as important. This same approach can be applied, as we did, to discuss transition between atomic states. We use hydrogen wave function as our example because we know those wave function form. But the same idea can be applied to transitions between molecular states. Now, that is something very big. By that, I mean the following. In a molecule, these states can be of different natures. There are electron states, meaning states for electrons to fill in according to the Pauli exclusion principle. That's what we did in atom. But molecules have something more than atom. For example, after the electrons are filled into molecules, there will be a density, electron density distribution, right? Now, you have two nuclei, electron distribute themselves. Wave function square. What do the electrons do? This distribution is what you used to draw as the spring. This comes from the electron's wave function. Okay, so when you are young, you learn molecules like this. There's a spring, okay? And in your classical mechanics, you have this model. But in a molecule, when we understand quantum mechanics, we now know what is this spring. This spring has to do with electron filling in molecular states. And with this spring, then we have something more than atom. That is the new element in molecular physics. The atom connected by a spring can vibrate. Okay? And that is observable in spectrum. Atoms do not have this. Molecules have this. Usually you see this in the infrared spectrum. Okay? That is more important in recent years because unfortunately, carbon dioxide now has become a bad guy. Everybody said it's a bad gas or a greenhouse gas. We should reduce carbon emission. Okay, all this. Actually, it means reduce CO2 emission. And then only with quantum mechanics and these transitions, we can understand why CO2, okay, is now regarded as the bad guy. Actually, no, it's neutral for him, right? For CO2. And suddenly you're telling me that I'm the bad guy. It has a vibrational particular frequency that hits at a very important range of sunlight entering and our Earth emitting. We emit at the right frequency of this CO2, a particular vibration. And because of that, CO2 can absorb that as the Earth emits its energy out, therefore trapping some of those heat. Okay, now that is quantum mechanical. And that is vibrational thing that we need to discuss in the next module. In addition, a molecule with a spring, the first approximation is to think as the spring as the rock, right? And thereby you have rotation. For example, water molecules can rotate at some particular frequency, okay? And you make good use of it. Microwave oven is at the microwave region, and this rotational frequency is in the microwave range. Therefore, you can put a glass of water into the microwave oven, not too long, maybe 2 minutes or so, you get a nice warm glass of water out, okay? That is rotation. All this vibrational and rotational thing add to the allowed energy levels for a molecule. Therefore, when we consider transition between vibrational levels, we again make use of the result. We have an initial state and a final state with something in between that decide whether this is allowed, that is not allowed, okay? So we will discuss it later, but it is one umbrella theory that works for all this. As you go to solid state physics, there is an optical property part, and in which, again, you will make use of this transition rate, this formula, initial final with something in between, to decide whether there is strong transition or not. Okay? So finally, for those who like theory more, you want to learn second order time-dependent perturbation theory. That is interesting but troublesome, okay? Not recommended at this level, but if you do, I would recommend these books, especially this one in great detail. You can find the derivation rather cleanly. For those who like the applied side more, the applied side of time-dependent perturbation theory, I recommend the book by Yarif, Introduction to Theory and Application of Quantum Mechanics. Yarif is famous for his contribution in laser, in quantum electronics. A more formal book by him, again, is Quantum Electronics. There are 24 chapters. I think you can conquer the first half readily after this module, okay? For those who want to go into so-called AMO, a very popular branch of physics now, at atom molecules and optics, for atomic physics part, a complete book for atomic physics. There are two, undergraduate level, this one by Mark Fox, rather nice. I think you can follow it completely now. Maybe you know more than this book in terms of theory. And if you want to go to the master level, beginning postgraduate level, this book by Christopher Foote is a standard beginning level specialized atomic physics book, including some discussion on outer cold atoms, how to cool down atoms to nano Kelvin. Okay, the thing that Professor Wang Dajun is doing in our lab. Okay, nano Kelvin, 10 to the minus 9. Okay, and this is a new development. That's why AMO suddenly become very hot in recent years. If you want to learn more, these two books will be a good starting point. All right, so that will put an end to the atomic and the atom-light interaction module. So we will have the midterm on Saturday. You have received an instruction face-to-face on campus. Just come on time. Take your temperature for yourself, okay? Report anomaly, and then go into the right room according to your last name. Bring something to clean your hand. You may want to just to feel safe, clean the desk, okay? And then we will start at 10 a.m., all right? So the coverage has already been announced much earlier, all right? So that ends today's class. I will stay on for some questions, so we are done now.